Okay, so let's take a look at equivalence relations. We know now that the properties of relations can be summarized as reflective, asymmetric, antisymmetric, or transitive. So using these concepts, we are able to define equivalence relations. And a relation on a set, remember, is again on a set A, is the same set, is called an equivalence relation if it's reflexive, symmetric, and transitive. Okay? So two elements A and B that are related by an equivalence relation are called equivalent. And we use this notation to say that these two elements are equivalent with respect to a particular equivalence relation. During the synchronous session, we'll revisit the congruence modulo. Remember your notes from the integers when we talk about congruences and modulo operations. So this would be a good time to go back and read about that before the synchronous session. Same as divisibility. So if you have a chance, go back to your notes, take a look at the integer section of the course. That would be useful for you to understand those two exercises. We have another definition here. That's the equivalent class. So we have this notation. So we have the square brackets. A is an element of A and the relation. The set of all elements that are related to an element A is called the equivalence class. Okay? Okay, so when we see the exercise in the synchronous session, make sure you come prepared and you know these concepts and ask your questions in real time. That would be very beneficial for the understanding of these topics. Okay, so so once we have the concept of equivalence classes, and then we can also take a look at partitions. Let's think about the Starfleet Academy example again. So we have X and Y are the students who got the same grade. So remember, if we go back, we had Riker and Worf getting the same grade on the course. So we would say that those two are related according to this relation. Now, the relation is an equivalence relation because it's reflective, reflexive. So that means that if X got the same grade as Y, then Y got the same grade as X, right? It is symmetric because if you look at the matrix for this relation, it's going to be a mirror matrix with respect to the main diagonal. And it's transitive because if X got the same grade as Y and Y got the same grade as Z, then X got the same grade as Z. So it has all these properties: reflexive, symmetric, and transitive. So it is an equivalence class. Okay, nothing new so far. Now, if you think about it, this relation R is actually splitting the set of students into a number of disjoint subsets. So that means that these subsets have no elements in common at all. And furthermore, each of those subsets is an equivalence relation, an equivalence class of R. So we have this theorem. So R is an equivalence relation on a set A. So when we say that these three are equivalent, it means that if we have any of these three, then the other two should be true as well. In the synchronous, we'll do this theorem, and as we go through the solution of this exercise, these concepts will be reinforced, and you'll have a chance to ask your questions in real time. We have another theorem that we'll see. So R is an equivalence relation on a set S. So remember, when we say an equivalence relation on a set S, that means we're talking about the same set, right? So the equivalence classes of R form a partition of S. And conversely, so if you have a partition of the set S, there is an equivalence relation R that has the sets A sub I as equivalence classes. So when we do this exercise in the synchronous, this theorem will become much more clear.